वसुंधरे त्वम् अस्मान् सर्वम् अयच्छत् वास्तवे अस्माकं योग्यतया कति अधिकः पर यदा त्वं कुपितः भवति तदा वयं निस्सहाय भवन्ति माते एतादृशः अवसरे अस्मान् ज्ञानस्य सद्बुद्धेश्च सहकारं कुरु। Natural disasters can occur at any time and at any place, causing loss of life and property on a massive scale. Global statistics show that between 1991 and 2005, some 10 lakh people were killed the world over, and property worth rupees 3 lakh crore was lost annually due to natural disasters. India's unique geoclimatic conditions make it extremely vulnerable to such calamities. Devastating earthquakes, floods, and cyclones are recurrent phenomena and result in the loss of property worth nearly 10,000 crore rupees every year. Another fallout of these disasters is the collapse of basic infrastructure, like roads, bridges, terrestrial communication, and electrical systems, which paralyzes life. Just look back at the last 10 years. The Orissa super cyclone, Bhuj earthquake, Kashmir earthquake, and the Mumbai floods all have contributed their best to make our lives difficult. We cannot stop a natural disaster, but we can surely reduce its consequences. It is in this context that technology and the people behind it play a vital role in dealing with disasters in all its phases. That is, pre-disaster, during disaster, and post-disaster relief work. The scientific community plays a silent yet extremely vital role in disaster management.
This is the information I want to send you.
Today, we are able to make near-accurate forecasts of certain disasters in the form of predictions and early warnings in certain cases like cyclones and floods. Monitoring disasters, assessing post-disaster damage, and providing communication support to the post-disaster relief operations have certainly strengthened the hands of civic and rescue authorities. Today, in India, there are several organizations like IMD, CWC, SERC, INCOIS, and ISRO, which are involved in active research and development related to disaster mitigation using sophisticated science and technology. India's high earthquake risk and vulnerability are evident from the fact that about 60% of its landmass is prone to earthquakes. One look at this map makes it clear that a major portion of the land area could face moderate to severe earthquakes. During the period 1990 to 2006, more than 23,000 lives were lost due to 6 major earthquakes. Uttarkashi 1991, Latur 1993, Jabalpur 1997, Chamoli 1999, Bhuj 2001, and Jammu and Kashmir 2005. Our scientific and technological community is working round the clock with a view to developing long-term and sustained methods of addressing this problem. At present, it is not possible to predict earthquakes, but with current scientific advancement combined with a proactive, holistic and integrated approach, we have been able to strengthen disaster preparedness, mitigation and emergency response. Constant monitoring of earthquake-related activities and communication of vital information on the occurrence of earthquakes to the disaster management authorities is carried out using sophisticated technology and through availability of refined modes of communication. An earthquake operational center is also functioning on a 24/7 basis in New Delhi. The center has the operational responsibility of keeping a round-the-clock watch on seismic activity in and around the country. A seismological observatory has been set up in the premises of Delhi University to observe the earthquakes occurring in and around Delhi in particular and globally in general. It sends reports immediately to the central receiving station at IMD New Delhi. This observatory is equipped with a conventional seismograph of world standards and state-of-the-art new technology based on the broadband seismograph. The seismological unit at the IMD Chennai comes under the Global Seismological Network. It is equipped with real-time seismic monitoring network, specially for tsunami-related inputs. The seismic data that is received is transmitted to INCOIS on a real-time basis. Studies of all the major earthquakes have established that casualties occur primarily due to the collapse of buildings. The Structural Engineering Research Center, Chennai, is a national laboratory under the Council of Scientific and Industrial Research. It has an advanced seismic testing and research laboratory which is developing solutions to problems arising out of seismic loading on civil and mechanical structures. Let's take a look at this shake table system on a rigid seismic mass. A test model of a particular civil structure is placed on a shake table which then generates an earthquake at a predefined Richter scale and makes the structure shake. A detailed study is then carried out to see how the structure has responded to the artificial earthquake. The research helps in developing new houses and material for improved earthquake-resistant performance. Floods have been one of the major causes of recurring disasters in the country. In a country where 40 million hectares of land is prone to floods, forecasting floods becomes a major step towards prevention and reduction of losses, both of lives and money. Forecasting floods in the major river basins of the country helps the civic authorities take timely preventive measures. To forecast floods, it is necessary to know the flow conditions in the upstream river and also the rainfall that has occurred in real time, so that the expected volume of water that is likely to reach the area of interest and cause flooding can be estimated. The idea is to maximize observational accuracy and reduce data acquisition time at the modeling centers to issue timely forecasts. Very fine technology comes to the aid of the scientists. Microprocessor-based modern rain gauges are used for measurement of rainfall using tip buckets principle, with each tip being recorded and processed by the control mechanism for computing the rainfall. Measurement of the water flow in a river channel is a very critical and extensive exercise. This is realized using sophisticated microprocessor-based electronically controlled bubble pressure gauges. Automation has moved a step further, and it is now possible to measure the reservoir water levels, relative humidity, wind speed and direction. All the data that is collected is then transmitted from the site to the modeling center without loss of accuracy within the shortest possible time. When the climatic conditions are also adverse, satellite-based communications come to the rescue. The ground stations located at strategic positions across the country receive the data reflected from the data relay transponder of the INSAT series of satellites. Each of the ground stations is capable of receiving data from about 800 different stations. The data is further distributed through satellite-based networks to the respective forecasting centers. Cyclonic storms contribute to a major chunk of the devastation caused by natural disasters. Most of the Indian east coast is prone to recurrent cyclones. An early warning to the concerned departments helps in dealing with this disaster most effectively. We have been able to develop a good network of surface observatories satisfying the requirements of the World Meteorological Organization. A number of automated weather stations are in operation along the coast and provide surface observations on an hourly basis, which are used in cyclone monitoring and forecasting. Frequent cloud imagery data received from our national satellites, Kalpana 1 and INSAT 3A, provide the unique capability of continuous monitoring of cyclones right from the early stage of inception to the maturity stage and up to the stage of landfall and even beyond after the dissipation stage. The warnings are disseminated through a variety of communication media such as radio, television, the print media, telephones, fax, telex, telegrams and police wireless networks. A specially designed cyclone warning dissemination system which works via the INSAT satellite provides area-specific service even when there is a failure of conventional communication channels. Regular bulletins are issued for utilization by the central and concerned state government authorities. This is a cyclone E-Atlas. IMD has prepared an integrated package on the tracks of cyclones and depressions that occurred over Indian seas between 1891 and 2007. This E-Atlas, which can be installed in a personal computer, proves to be a handy tool for tropical cyclone forecasters, research workers and disaster management experts. IMD has a state-of-the-art Doppler weather radar facility in Chennai. Using this radar, the atmosphere near Chennai within a radius of 400 kilometers can be kept under surveillance. This radar helps us in detecting cyclones, microbursts, severe thunderstorms and hailstorms. This facility is extremely helpful in nowcasting, flood warning and general weather forecasting. Cyclones inflict considerable damage on small dwellings such as hutments and other traditionally built structures. Even though it is not possible to totally avoid damage to these structures during severe cyclonic storms, the resistance of these structures can be significantly improved by adopting preventive measures at the planning and construction stages. Cyclone disaster mitigation has been one of the thrust areas of R&D at SERC Chennai. The facility here offers testing of structures and structural components, R&D in the field of wind engineering, assessment of wind loads, and the dynamic response of the structures. This in turn helps scientists in understanding the behavior of cyclones. Today, with extensive R&D, we have been able to develop safe and economical cyclone-proof designs for a variety of buildings and structures such as residential dwellings, tall chimneys, communication towers, etc. Here we see a state-of-the-art boundary layer wind tunnel facility for testing of models of buildings and structures in simulated atmospheric flows. The tunnel simulates strong wind conditions and helps scientists study its effect on various structures. All the programs in the wind tunnel are fully automated and computer controlled. The maximum wind speed attainable is 198 km per hour. All this helps in designing extremely wind-safe dwellings. The word tsunami in Japanese means harbor wave and is used as the scientific term for a class of abnormal sea waves that can cause catastrophic damage when they hit a coastline. Tsunamis are caused primarily by earthquakes occurring below or near seafloor. The tsunami that struck the Andaman and Nicobar Islands has left a permanent impression in our minds of the extreme devastation that nature can wreak. An early warning system can be of great help to nearly 40 crore of our population. This is the segment that lives in the coastal belt in the constant shadow of this oceanographic disaster. In light of this, the Ministry of Earth Sciences has set up the National Tsunami Early Warning Center at Incois, Hyderabad. All this necessary computational and communication infrastructure enables reception of real-time satellite data from all the sensors, analysis of the data, generation and dissemination of tsunami advisories following a standard operating procedure. The Indian Tsunami Early Warning System comprises a real-time network of seismic stations, bottom pressure recorders and tide gauges to detect tsunami-genic earthquakes and to monitor tsunamis. The Early Warning Center receives real-time seismic data from the National Seismic Network of the Indian Meteorological Department and other international seismic networks. The system detects all earthquake events of more than magnitude 6 on the Richter scale occurring in the Indian Ocean within less than 15 minutes of occurrence. Seismic and sea level data is continuously monitored in the Early Warning Center using a custom-built software application that generates alarms or alerts in the warning center whenever a preset threshold is crossed. Tsunami warnings or watches are then generated based on preset decision support rules and disseminated to the concerned authorities for action following a standard operating procedure. This is how an early warning can help in coastal evacuation to safe shelters. Services based on space systems and information derived from satellite data can provide support to disaster management activities. The Department of Space, Government of India, has been developing techniques and methodology by integrating space-based systems and services for disaster management. The DMS program of ISRO is based on its space-based assets in the form of remote sensing satellites, meteorological satellites, and communication satellites. The remote sensing satellites provide a synoptic view of the flood-affected areas at frequent intervals for assessing the progression and recession of flood inundation. The low-pressure areas in the high seas, development of a cyclone, and the track of the cyclone are monitored by the meteorological satellites of ISRO. Communication satellites can provide vital communication links to the people of the affected areas and also to the disaster management and relief authorities. The DMS program mainly addresses 5 issues. 1. Creation of digital databases at appropriate scales for facilitating hazard zonation, damage assessment, etc. in perennially disaster-prone areas. 2. Development of appropriate remote sensing and geographical information system-based decision support tools and techniques and demonstration catering to information needs at different levels. 3. Acquisition of close contour information for priority areas. 4. Strengthening the communications backbone for addressing the real-time information transfer needs. And 5. Networking of scientific institutions for exchange of data, information and knowledge. The modern and state-of-the-art Decision Support Center is built at NRSC, Hyderabad. It is a single-window delivery point for space-enabled inputs used in all 3 phases of disaster.
Delivered to you from Decision Support Center are useful. And exactly this is separate information. What GSI is doing for identifying the hazard zone areas.
A number of field deployable communication terminals are developed for use during disasters. INSAT MSS Type C terminal, INSAT MSS Type D terminal, which is a 2-way satellite phone, Fisherman Distress Alert System, which works in UHF band, are all examples of such devices developed by the Space Applications Center of ISRO. The objective is to evolve a community that is informed, resilient, and prepared to face such disasters in future with a minimal loss of lives and damage to property, assets, and infrastructure. In the past, our space-based assets have helped during post-disaster relief activities after the earthquake in Bhuj, after the super cyclone in Orissa, and after the strike of tsunami on the Andaman and Nicobar Islands. These examples highlight the value of the information and services provided by our SNT community to society in the service of our people.